Okay, so let's start this session on computer vision. Okay, we will start with the first talk by Bhalaji Nagarajan, that it's learning multi-subset of classes for fine-grained food recognition. Thanks.
Good afternoon, everyone. So this is our work on learning multi-subset of classes for fine-grained food recognition. This was a work in collaboration with Javi, Mark, and Petia. I am Bhalaji. I am the PhD student at the University of Barcelona. So this work was published in ACM Multimedia this year. So we will introduce the first, we will first introduce the problem which we are trying to tackle, and then we will talk about each component of a proposed framework. So the challenge here is fine-grained image recognition. So of late, fine-grained recognition is an ongoing research where we are trying to classify subset of classes which are very hard, even at in some cases, even for humans to classify them. So how does a model try to classify this is the challenge. So we are trying to focus on this hard to distinguish classes, and then we are trying to create automated methods which could basically learn to discriminate these particular classes. So this is the difference between a coarse-grained and a fine-grained class, where you have easy to distinguish classes in a coarse-grained classification, and where else you see it is hard to distinguish the classes of dogs or classes of birds in a fine-grained challenge. So the traditional approach is to focus on those regions which are very obvious to distinguish between these classes, and in the traditional approach, all classes are treated in the same way. Of late, there have been two recent lines of research where you try to have an hierarchical approach, where you learn the features from the coarse classes and then you fine-tune for your fine-grained classes. And another one is the path-based localization, where you try to learn only those regions which are very discriminative to each other. And recently, there have been hybrid approaches between the two. So this is in fine-grained recognition in general. Food recognition, which is by itself a very difficult computer vision problem. So here, each of us could cook the food differently. So the same food you could cook differently and I could cook differently. A food such as a carpaccio or a tomato salad are visually very similar to each other. And also if you look at classes of beans which are visually very similar but semantically very different. So the aim is for an algorithm to differentiate between these classes. So how do we basically identify this particular group of classes, and then how do you basically make this prediction out of this? So this is basically the design questions which you are trying to address in this work. So in our proposed framework, we basically have a normal baseline which is nothing but a transfer learn model, and then we try to use the learning of this model to cluster different classes and basically have a hierarchical multi-head training where you try to learn individual clusters differently. And finally, we have a prediction layer which is going to combine the output of the subsets. So we will see each of this in detail. So the first part is to create classes, the subset of classes. So after you basically train a model, which we call as a baseline, so we basically get the confusion matrix, and then we try to convert this into a distance metric using the formula here. So this metric will allow us to identify the classes which are very confusing to each other. So now with this distance, we basically apply clustering, and then we take a thresholding to take only those clusters which are meaningful. In a clustering, you will basically have a lot of classes which are not meaningful. So we basically apply a thresholding, and then we basically get only those classes which are very confusing to each other. So this is an example of the clustered classes. So here we have classes of eggs which are very similar to each other and which are identified as a classes in the cluster. And this is the TSNE of the classes. So if you could see, the clusters are very close to each other and are hard to distinguish. So now what we do, after we identify these clusters, we basically replicate the block of the learning algorithm. So in this case, we are showing this with a transformer. So we basically replicate the transformer blocks, the last blocks, as many times as your subset. So what we basically do, we freeze the rest of the layers, and then we try to learn only this subset classes. So here there is the subsets will also have classes which are not belonging to the subset, so that your model also learns the representation of your original data. So with this, you basically have a model which is going to have different heads for each of the clusters, along with a cluster head for the original classification. And then basically we use the cross entropy loss for each of the heads, and then we basically average it out for the final loss. So here there is a problem where you have the problem of imbalance. So there is going to be an imbalance within the clusters, and also there is going to be an imbalance outside the clusters. So how do we tackle this? We basically use a subsampling method where we try to use median of the classes, and then we basically train each of this clusters separately. So the next question is, how do we get the output from each of these heads? So we basically use a fully connected layer, and then the output of each of the classes are basically mapped to the final classes. So here there will be n classes at the end. So here there are two types of initialization we do, where we do the normal initialization, like random initialization for each of the clusters, and then we do identity matrix initialization for the original class. So this is to make sure that you are not degrading the performance, you are only improving from the baseline performance. So once we have this model, we basically try to evaluate this on different datasets. So here we have three datasets, the common food datasets, the food 101 which has 101 classes, the food X 251 which has 251 classes, and food 1K has 1000 classes. The food 1K is the largest available class. So we try to apply this on two transformers, the state-of-the-art transformers, the CSWin and VOLO, and we were able to implement this. So the details of implementation is this. So we basically use hierarchical clustering for the subset construction, and then we basically use the median of the largest vertical distance as a thresholding metric, and then we replicated only the last blocks of the transformers, and then we combine this along with other approaches like the gradient accumulation and test time data augmentation, which further boosted our performances. So this is the performances of each of the data set. So if you could see, we are basically bettered in all the experiments compared to the baseline, and particularly on food 101, we are right now the largest, like we are the top performing model on food 101, which without using additional data, and we are like globally ranked third on this particular data set. The other two data sets are challenge data sets at different conferences, and we were able to achieve comparable performance with the other leaderboard positions. And we basically did several ablations here. One is to identify the number of clusters. So based on the thresholding, you identify how many clusters work, and we also try to use different components of this method for our ablation. So particularly this method is very time consuming because we are basically doing it in different stages, and it is a very complex model. So these are two particular limitations which we found during the publication of this paper, which we are trying to further research on. So in conclusion, we basically try to address fine-grained recognition applied on food recognition, where you have the inter-class differences are pretty small, and we proposed a multi-subset clustering technique, which is going to learn better the classes inside the cluster. And we were able to validate it on different data sets and able to get better performances in all the experiments which we did. Yeah, thank you.
Okay, so there's any question from the audience?
Hi, thank you for your presentation. It was a very nice presentation. So I have two questions. Both are related. So the first one would be, how do you train the baseline, the first transformer? Because the second question is, which of the two parts, you said it's very time consuming training this model, which of the two parts, the baseline or the fine-grained part, is more time consuming? Thank you.
Yeah, so the first part is normal transfer learning. So we basically took the state-of-the-art transformers and applied it on our data set. The time consuming part is you basically train the baseline and then you have to decide on the clustering and then you need to retrain it. The good thing we found is you need not train the entire block, but you just need to train the subset blocks and then the final decision making block. The time consuming part is this. So you train a baseline, which is already a time consuming one, and then you need to make the decisions with the clustering and then do another set of training. So it's a combination of all.
Okay, thank you.
Is there any other question? Okay, I have one question. Have you performed any qualitative analysis of the clusters that you are obtaining for these subsets?
Yeah, so basically we did the qualitative analysis. So we were able to see that whatever we identify as clusters are meaningful. For example, if you identify a cluster which has all meat, it was actually the meats which are more confusing. So qualitatively it was proven.
Okay, so let's thank the speaker.
I have another question. Yep, sorry.
Okay. Sorry.
Well, since the difference between every class could be, well, both semantic and visually, I wonder if some classes can be separately, I mean the very same class of the baseline can be separated into different clusters to better perform performance later. I don't know if I've been clear.
Can you rephrase it?
Yeah, I mean, imagine that a class is, I don't know, some kind of omelette that can be served in two different ways, and visually, or I don't know how, but it would end up being in two different clusters, but the very same class visually is in two separate, or can be separated in two clusters. So have you considered this separation, that it is not between classes of the baseline, but between, I don't know, it's more detailed?
We have, like not in this work, but we have different works where we try to address this intra-class differences with different approaches. But in here we tried it with the visual similarities, also with semantic similarities. But here it is more derived using the labels.
Okay, thank you.
Okay, so let's thank the speaker again. Now we move to the next speaker, Eric Arazo from Insight in Dublin, with his work embedding contrastive unsupervised features to cluster in and out of distribution noise in corrupted image datasets.
Thank you, Carlos. Yes, I'm Eric Arazo, and I'm working in Dublin City University, and I'm going to present our paper from this last ECCV. And basically, it's a work on label noise, and I will start with a small introduction on what's label noise and how we usually address the problem. So as you know, when we train neural networks, we'll need large amount of data, and to do that, to collect that data, usually there's an initial step of gathering all the data, and then there's a second one where the data has to be annotated. And this process often results in wrong labels that we usually call noisy labels. And as a result, when we train neural networks on those data sets, the performance decrease. So this is something that we want to address. And as you can see in the cartoon, we would expect to have a label of a dog, but we have a label of a cat, so that's going to give a wrong signal to the backpropagation algorithm, and this is what we are trying to address here. The literature in general, it's quite wide, but we can split it into two big groups. One group of approaches that first try to detect which are the clean and which are the noisy samples, the clean being the samples that are correctly labeled, and the noisy ones, the ones that are not. And then they have usually a second stage where they try to correct that, or propose some sort of compensation on those errors in the data set. And then there's the other group of approaches where they directly learn from the noisy data set with some sort of robust loss that already accounts for that noise. So we will focus on the first one. Well, our approach falls on this category. And in particular, we will focus on the scenario where we have labeled, gathered from the data directly, and the annotation process it has very few intervention from humans. So this data usually is collected by searching some queries online and then downloading data directly and using those queries as labels. And as you can imagine, this results in very noisy data sets. In particular, we have three kind of samples: clean samples where the query corresponds with the image, so it's correct. Then we have some in distribution noisy samples where the label is wrong, so the query it doesn't correspond with the image, but that query corresponds with some other class in the data set. And then we have the most challenging group or most challenging noise that we find is the out of distribution noise, where the label and the image doesn't correspond, but on top of that, the image doesn't have anything to do with the data that we care of. In this simple example, we are trying to distinguish between cat and dog, and we have the clean sample there, the cat with a blue square that's correctly labeled. Then we have the dog that it's labeled as a cat, and it's in purple because it's in distribution noise, because the label it's in our distribution of labels, that it's cat and dog. And then we have the third one that it's a chair, and that's the out of distribution noise because the true label is not in our distribution, and the images themselves doesn't have anything to do with the problem that we are tackling. So the main contribution of our paper is the observation that when we pre-train neural networks with contrastive approaches, in particular unsupervised contrastive approaches, the feature space that we generate, it's naturally split, and the samples that are out of distribution fall together in a cluster. And as you may know, when we train usually contrastive approaches, we usually do a L2 normalization at the end, so we make sure that the features fall in a hypersphere. And this is a representation of that hypersphere in 2 dimensions. And as you can see, all the red samples are together on top of there, and all the rest ones are distributed across the sphere, and the red ones are the out of distribution. So that's some sort of a visualization of what happens in the feature space when we learn in a contrastive approach. And a bit more quantitative experiments is this table where we trained a linear classifier to identify clean and noisy samples. And in most of the experiments, the accuracy of detecting noisy and clean samples have over 95% of accuracy, showing that there's actually a linear separation between the in distribution and out of distribution samples. Then our approach has a second stage where once we have trained this contrastive approach at the beginning, then we use this spectral embedding to automatically detect these three clusters that are the in distribution and out of distribution, as well as the clean samples. And then that's our clean noise detection that we then use to train the model. And we particularly, in the training stage, we try to leverage all the samples that we have. Most of the common approaches try to discard the out of distribution samples because usually they don't bring that much to the training, but we show that they do. So what we do with the in distribution noisy samples is to correct their sample by averaging the prediction of the model in 2 different augmented views of the same image. That's what you see here in the Y sub I. Then the tau sub 1 is just a sharpening of the label that helps training the model. And then with the out of distribution sample, we use a contrastive loss that helps the model to learn more basic features. And for example, what you can see here, that these images are not related to our tasks, but they help the model to learn these basic feature detectors, like in this case, these vertical lines that help to have a more robust performance. And as you can see here, this is reflected now in the results. So our result is this one here, and we have around 0.5 improvement in top 1 accuracy, but most importantly, we have around 2 points of improvement in the top 5 accuracy, showing that the model is leveraging this more semantically meaningful structure that we get from using the contrastive loss in the out-of-distribution samples. And thank you very much for listening, and I'll be happy to answer any questions.
Thank you, Eric. Any question from the audience?
Thanks for the presentation. My question is, like, did you try to validate how the out-of-distribution samples work if you remove them and the way you train it?
Yeah, we have some ablation studies in the paper where we train with and without the contrastive learning loss. And you can see that there's an improvement on the performance when we just correct the samples and we don't have these additional loss that we have here, when we have only the correction there, and then when we introduce the contrastive loss, we have a small improvement.
The other question is, like, when you have an out-of-distribution noise, it's basically something which should not be present in the data set, no? So how does this model leverage from this? Like, why should it, like, theoretically, why should it learn from this? Because it is nowhere related to what that problem we have.
Yeah, our hypothesis is that the model is learning these low-level features like edges or circles or these vertical lines that help to have a more robust initial layers. So our hypothesis is that the improvements are not in the later layers that are more related to the classes, but in the initial ones that are more basic or more low-level feature.
Thanks.
Thank you.
Thanks for the presentation. I have a simple question. What was the proportion of these noisy labels that you added, like the out of distribution and in distribution? And how does it affect if you test it with the amount of out of distribution noisy labels, for example?
Yeah, we vary the amount of noisy labels, and as you can see here in the R sub out, this is the proportion of out of distribution samples, and yeah, the more noise you have, the worse will be the results. You cannot really see it here because it's just the detection of clean and noisy, but this is then later reflected on the accuracy here. This is for mini web vision and ImageNet 12, that it's already corrupted. But we have, so all of these experiments are with a single noise ratio, but usually all of these papers comparing, you have big tables with all the different ratios of noise, and you can see the more noise you have, the performance will be worse, both in distribution and out of distribution. Thank you.
Okay, is there any other question? Okay, so let's thank the speaker again, and we will move to the next presentation.
Okay. My name is Debora Gil, and I will present BronchoPose, that is our approach for doing camera pose estimation in bronchoscopic videos. The background and the motivation is one of the best ways of getting a sample for doing biopsy in lung cancer is performing a bronchoscopic procedure, okay, in which the clinician navigates through the bronchi by means of a bronchoscope, which is a flexible tube with a camera mounted on the tip, and that provides the physician an internal view of airways. And the goal is to reach the lesion that has to be biopsied in order to know if they are malignant or not. Now, is to repeat the path that the physician has previously planned offline. And currently, this is achieved by doing a visual inspection of 2D fluoroscopy straight image. Obviously, this is far from optimal, and in 30% of the cases, the intervention has to be repeated because it leads to inconclusive results. Now, what we propose to do, and which is the future of guided interventions, is to do a video-based guidance so that in the interventional video, in real time, we would display and indicate the doctor which is the best way to reach the lesion, and thus helping him to reproduce the previously planned intervention. Now, in general, we have two main contributions to the estimation of camera pose in video bronchoscopy. The first one is a synthetic database based on a digital twin of the patient. Then we evaluated different metrics for the loss and evaluation of the camera orientation, because a camera pose, you have to estimate both the position and the orientation of the camera. And the metrics for, the metrics for the orientation, we did an analysis so that we make sure that we are exactly evaluating the difference between the estimated and the ground truth orientations. Then we did also an analysis on what was the best way of processing temporal information, because video bronchoscopy, it's a video, and we have several ways of trying to incorporate this information to the final prediction. And finally, we addressed several levels of population modeling, because in the field of medical imaging, one can have two options: to get a generalist population model or a model personalized for each patient. And in our case, in these applications, this is a perfectly reasonable assumption. So the synthetic data set that we produced and that it's available on our webpage consisted on several videos simulated from an anatomy of bronchial airways, extracted from CT scans from several patients. These CT scans, the segmentation of the bronchi, were codified using a graph, and then we used this graph that was codified in the main anatomy to produce several trajectories. Some of them were corrupted with several amounts of noise, both in the central navigation path and also in the orientation of the camera. That for the central and corrupted path was along the trajectory. Now, all these trajectories that were extracted from 15 patients were used to train several models. The models that we trained were regression models, where the output of the network was the difference in position and orientation between two consecutive frames, if we have a tracking, or from the central navigation path and the corrupted navigation that would be the one that the doctor would perform in general. Since we have difference in positions and in orientations, one should take into account that the orientations are not 3 magnitudes in the Euclidean space. So then we could consider metrics for measuring this difference different from the mean square error, which is based on the distances on the Euclidean space. Since we are not in the Euclidean space, we consider some distances on the sphere. Okay? These two distances were the cosine, inverse cosine, between the vectors, the ground truth vector associated to the rotation given by this 3 angles, and the vector predicted by our system. And also we consider a distance that was directly the cosine of the difference between the ground truth and the estimated angles. All these 3 angles, I didn't say it, but they correspond to the Euler angles of the rotation in 3D space. Concerning the architectures, we took into account 4 different architectures. One backbone baseline static architecture that was taken as input to different frames, and was the output was the difference between their position and orientation. Then we considered 3 different architectures incorporating temporal information. The first one that was flattening the features from the last layer of the static backbone architecture, and this was the input for an LSTM recurrent neural network. And 2 more architectures that were taking into account also the structural images, because if we flatten the last layer, then we might be losing the geometry and the appearance of images. And these 2 are these 2 last networks, one that was a convolutional LSTM, and the other one that was directly a 3D convolutional network, where the time was considered as a new dimension. Finally, concerning the modeling of population, we have 2 different options. First one, that would be a population approach, where we train the system with some cases that would be trajectories from a given set of patients, and then we test the system on an unseen subject. Okay, this would be the more generalist approach, but not necessarily the best one. Another option, and since we are dealing with a clinical application, would be to train on a set of patients and then test the system on a new trajectory from the same set of patients. That would be a reasonable approach, because the trained set of patients and trajectories would be the planning of the intervention, and then the test would be the intervention itself. So it's an approach that in medical imaging, in intervention guiding, is a good one. Experiments. We did 3 different kind of experiments. The first 2 were to set the best configuration of the system in terms of the architecture and losses used to train it. Then the best performance of the first experiment, and this in a personalized setting. The best performers of the first experiment were trained on a population approach in a leave one patient out setting. And finally, the best of the models from the first and the second experiment were compared to the state of the art. We used the 3 metrics that we developed, or we want to analyze for assessing the orientation of the quality of the orientation predicted by each system. Results. Here we have the results of the best methods, architectures, and losses from the first experiment. For the tracking and a calibration setting, we would be assessing the difference between 2 consecutive frames, and in a calibration setting, we would accumulate the estimated position and orientation for the whole sequence, and then compare the final errors. In red, we have the best performance, and the blue, the second best. As you can see, definitely models taken into account as expected. Temporal information perform better, but also those methods that take into account also the structure of images, so that we don't do a flattening of the last convolutional layer of the baseline architecture, also perform better than the ones that do a flattening. That was also expected. Then the comparison to the state of the art, we also achieve better errors in both position and camera orientation. And here you have some examples of the predicted, of the ground truth trajectory in green, the predicted by our system in blue, and the one predicted by the state of the art, where you can see that there is a significant deviation from the ground truth trajectory, and even in some cases it goes outside the bronchi. This is definitely a very bad error, because then you would be guiding the physician outside the expected track. Okay. And well, what we can conclude, it's that digital twins are a powerful tool for providing data for training deep models and medical applications. This is very important because in the medical setting, we don't have data, okay? We don't have enough data to train powerful deep architectures, and there is a need of doing some sort of data augmentation in a sensible way. Now, simulations based on digital twins can be a means of doing this. Then, concerning tracking of a camera pose in interventions, temporal information obviously helps in producing better results. And the further steps would be to include other kind of models for doing tracking, like transformers, and compare it to commercial systems. And that's all. Thank you very much for your attention, and I'm here for questions.
Any question from the audience?
Thank you. This synthetic dataset, is it based on some sort of phantom, or is it fully computer generated?
No, this synthetic database is based on the segmentation of through CT scans. So it's not a phantom, it's based on real data.
Any other question? Okay, I have one that related with your last conclusion. How far do you think that are from applying this to real interventions?
This system could be already applied, but in order to get more accurate guidance, I didn't say it, but we are working on an hybrid system that combines images with inertial sensors. Okay. So this one could be already applied, showing very simple instructions to clinicians, but to be effective, we will need some more work. But okay, the image-based, ready to use. So if someone of you wants to use it, we have a very nice application, and we are ready to deploy it in any hospital you work with. Thanks.
Okay, so let's move to next speaker. That is Alexandra Gomez Villa from Computer Vision Center with her talk, Continually Learning Self-Supervised Representation with Projected Functional Regularization.
Hello? Yeah. Okay, so nice to meet you. So today I'm going to present this paper that we present at CVPR. So first thing I'm gonna do is to briefly describe continual learning for those of you who have never listened about this type of learning approach. So usually in computer vision and in general in classification, we learn this way. We have like a whole set of classes all mixed in a one data set, and then we learn everything at the same time using your favorite backbone, transformer, whatever. But continual learning is about learning in a continual way, in the sense that we receive the data in a sets. So for instance, for task 1, we receive these 2 classes, and for other tasks, let's say second task, we receive these other 2 classes. So what we really want to do here is to not forget the knowledge about the first task when we are training in the knowledge of this second task. But of course, we are usually, it depends on the setup, we are not going to receive any data from task 1. So you don't have to forget the previous knowledge at the same time that you are learning new knowledge. So there are like flavors of doing this. For instance, in task incremental learning, which you can see the cat is a little bigger, you have a task ID, which means that when you receive the data from your first task, what you are going to have is an ID that is going to tell you, okay, all of this data of this task is task 1. And when you're training on the next task, you are going to see another task. At the moment when you are going to perform any classification, this is going to tell you, okay, I am going to ask you which class is this image which belongs to the task number 2. So you can use that number to go to feed your classifier, to select a classifier. So that's kind of easy, and it's kind of have a really good result nowadays. The next one is the class incremental learning, the second one. In the second one, now you don't have any task ID. So you are going to receive any image at the same moment, and you really don't know when you did learn that class. You really don't know the set at which that class belongs, but but you have to either way classify correctly. And then there is representation learning, which is about, this paper is about, in which you don't even have a label. You don't know each class, if it's a cat, it's a dog, you don't have anything about. You only receive sets of different tasks, which belongs to different classes, but either way you have to perform learning without forget previous data. And then there is like the final goal, which is mostly human learning, in which it's online continual learning, in which you receive a stream of data and you learn continuously in each set of images that you receive. So depending on what you are going to do, there is like things that you can perform. For instance, if you are going to learn a new task without using any samples from previous task, this is an exemplar-free method, which is really difficult to perform your task. But maybe you can use samples from previous class. You have some memory, something like that, and you can save actually something. And then you have replay methods. And that replay methods have something that is the number of exemplar, which is the number of samples. And if you have more samples from previous classes, then you are approximating to joint training, and it's easier to perform continual learning. Okay, but why we are interested in continual learning? Well, learning in real world is actually difficult. And what is common is to really don't have any task ID, any separation between classes, which is not as boundary. The data is usually not well distributed. There is, of course, the labeling cost. So continual learning already faced the evaluation without task ID and the non-identical distributed data. And for the labeling cost, we already know about self-supervised learning, which, as most of you probably know, have really good performance in a self-supervised manner compared against supervised method in accuracy. So we know that we can use self-supervised learning, and we need to mix it with continual learning. So there are a lot of contrastive learning or self-supervised learning approaches. Probably you heard about Sinclair, SimSci, Barlow twins, and you can go. Now there are Dino, Big Reg, and other methods that even use Transformer right now. So for this work, we are mostly interested in use Barlow twins, but we are going to show that our method is independent to use it with any of these two self-supervised methods. Okay, so continual learning already know how to solve this. There are already methods to do continual learning in a supervised way. So there are really two well-known methods, learning without forgetting, LWF, and elastic weight consolidation. Really briefly, what these methods actually do is, learning without forgetting, what it's doing is just a distillation, in which you have a teacher network, which is the model from your last task, and your student network is your model from the current task. So when you receive a new set of data, you are learning in a new task, what you actually do is to perform distillation from the teacher to the student network while you are receiving the current data. So that way you are close to the teacher at the same time that you are learning in your new data. And the elastic weight consolidation is also doing a distillation, but actually for the distillation uses something which is called feature information matrix to compute the importance of the weight of that should be changes or not in the student network. Okay, but this works for supervised learning. So what we first do is to adapt these two methods to unsupervised learning, changing that there is not any dependency of labels. So as you can see here, the gray square is the Barlow twins framework. There is no any different there. It's just Barlow twins. And outside the Barlow twins is the adaptation for the new method. So for here, you can see that we are doing a distillation between the teacher, which is the past backbone, and the current backbone. For actually do the distillation, we use the output of the backbones. That way, you don't need any labels. And for elastic weight consolidation, we need to know the weight importance. So we need some kind of loss. Instead of using any supervised loss, we use the Barlow twins loss, which is an unsupervised one, and in that way, we can perform two methods in an unsupervised way. But this is not enough. We are going to show you that if you use these two methods directly, you can get better results if you use our very little modification, which is called projector functional regularization. So what we have here is just the learning with a forgetting framework. It's exactly the same. The only difference is that green square that you see there. So the green square is going to project the representation of the current method of the current backbone to the space of the previous backbone. So in that way, the current backbone has added some liberty, some elasticity to adapt to the old knowledge. As you can see here the loss. This part right here is the contrastive loss, and then we have the linear without forgetting part, or the projector functional regularization, which the only adaptation is to add our projector M in the output of the backbone representations. So results. So if we pre-train the Barlow twins in Cypher 100, we split it in 4 tasks. So you first learn one task, then the other, then the other. And in the bottom, you can see the FT, the fine-tuning method. Fine-tuning is not doing anything. You receive one task, and then you learn in the next task without doing anything. So it's probably you are going to forget something. So what you can see in the FT is that the accuracy is more or less constant. It's 53, 53. It's because it's forgetting the previous knowledge, learning new knowledge. So in general, the accuracy in whole task is kind of the same. In the top, you can see the single and continual join, which is the joint training is our normal way of learning, using all tasks at the same time, which is the top performance. It's 55. That's okay. That should be the top. And you can see feature distillation FD is linear with unforgetting is 57 at the end of task 4. EWC is 55, and our method PFR is 59. Then here we use downstream classification, so we use the pre-trained network and just perform downstream classification in SVHN. And as you can see, our method is best in comparison with others. What is interesting here that is mentioned about other papers is when you perform downstream classification in continual learning in this way, you can even surpass the knowledge of the single training. This is something that is observed, that is commented in our paper and in another 2 or 3 papers. We still don't know why. The other papers neither know why, but okay, it's an interesting observation. Here we can see some task hour matrices, and we can see that PFR actually, in the task 1, you can see here the feature distillation is forgetting, it's 81, 78, 78, 77, but PFR is continually learning, it's 81, 81, 80, and 82. And also we have backward transfer. I'm not going to the details, but you can go to the paper and see that. We can see here results with other self-supervised learnings, with self-supervised frameworks as SynClear and SynScience. And you can see that it also works well, compared against fine-tuning. And here we have results with another dataset, TinyImageNet. Again, we pre-train in TinyImageNet and then perform downstream classification to show that it's actually our method is better. This is something interesting. It's called the forgetting versus intransigence. So in continual learning, you really don't want to forget. So you want to be close to this point, and you really want to adapt to new data. So you want to be as close as possible to this point of the graph. And we can see here several methods, feature distillation, PFR, and EWC with several parameters to maintain previous knowledge. You can see here in Cypher that PFR is better, but it's more impressive in TinyImageNet, because actually feature distillation is pretty far away from the performance of feature distillation is pretty far away of the performance of PFR. And finally, so what happens if you try with even more tasks? So we try with 4 tasks, but what happens if you go to 50 tasks or 100 tasks even? So as you can see here, find the feature distillation, which is in violet and brown, is the performance when you go to more classes, 150, is below the performance of PFR, which is green and red. So even with this high number of split, our method is better. And finally, the conclusion, okay, we propose a new exemplar-free method for continual unsupervised representation learning. We evaluated in several data and scenarios and proved that our results are better than just adapting the current continual learning methods to unsupervised setup. And our method is generic, and it can work with any framework self-supervised learning. As a future, okay, maybe try no task boundary in which the tasks are not splitted exactly. Maybe use some VITs to experiment with this. How can this could work? And maybe try with some exemplars. Maybe it will be better or not. And of course, we don't have any analysis yet, but we need to investigate why the projector works so good here. And that will be everything. Thanks.
Thank you. So, any question from the audience?
Hi, very good presentation. I'm just curious, could this approach be applied to other self-supervised methods that use exponential moving average, for example, BIOL?
Yeah, actually there is some papers that already try this with BIOL or MOCO, yeah.
And this distillation part is applied to the momentum encoder or the online encoder? Which of the branches?
I think it's for not the momentum.
Okay.
But yeah, but I'm not sure at this moment, but I think so. But you can go and see probably those papers.
Okay, thanks.
Yeah, thanks for the presentation, very good. Perhaps my question is a bit more general, but if I understood correctly, then the main contribution of this projector that you were mentioning is that you are no longer trying to keep these learned feature space from the previous model into the new one, so once you learn these new classes, but you are learning it up to a certain projection that you learn. That's why it's more powerful, because you're not keeping the same feature space as before, but just a projection of it?
Yeah, at the end, it's because it's more elastic, because it allows the current background to be more elastic, because you have like this flexibility to change, to adapt more to the current data, because there is a projector there that is going to put you closer to the old knowledge. Yeah.
Okay. Okay. Thank you for the clarification.
Any other question? Okay, so let's thank the speaker again, and let's move to the last presentation. So last speaker is Juan from INRIA with the talk that it's titled Multi-Person Extreme Motion Prediction, that has been presented in CVPR this year.
Hi, I'm Wen, and I'm a PhD student in Ely and also INRIA in France. So the work I would like to present today is multi-person extreme motion prediction. So in fact, I would like to present 2 works. The first one is a work in CVPR 2022, and the second one is called Back to MLP, a sample baseline for human motion prediction. It's a more recent work accepted by WACV 2023. And it's motivated and highly related to the first work. So let's start from the first one. Globally, in this work, we have proposed a new data set and a new baseline method for collaborative motion prediction. So what is motion prediction? We can see in this figure that what we want to do is that we take a sequence of observed human skeleton sequences, and by a predictor we would like to output the future possible skeleton movement of the skeletons. So this task is deterministic. So what we want is to let the prediction result as similar as the ground truth. Well, previous works about human motion prediction is mainly for single person, but there's no work starting multi-person human prediction. But as we know, our human beings, when we human beings understand the world, especially for multi-person scenarios, how we understand a person, a movement of a person is very highly related to the surroundings of it, but it's not just depending on the person itself, especially when there are some people involved in activity which requires very closely collaboration. How we understand the motion is highly dependent on the other persons. So the motivation of this work is to study if we could use the interaction information of the different persons to improve the motion prediction performance. But the first problem we have to solve is the data leaking problem, because the current available public data sets for 3D human motion is mainly for single person or multi-person, but just for some daily activities. For example, there are two persons standing together, walking together, or walking toward each other. So the interaction between them is not close and is not suitable for starting interacted motion prediction. So that's why we collected our own data sets, the extreme pose interaction data set. We call it XPi data set. And in this data set, our actors has performed a dancing action called Landy Hop. So in this kind of dance, the two dancers are involved very well. They are depending on each other very closely, and also the actions in this data set is very extreme. So we can see some. Sorry, no. Yeah, we can see some samples here in our data set. These are some actions selected from our data, and we can see the actions are very challenging. And also in this data set, we also provided both the different RGB videos from 68 different views, and also the mesh data, the mockup 3D data. So it will be a proper data set for doing not only motion prediction, but also pose estimation and shape reconstruction, etc. But in this work, we only use the 3D mockup data to do the multi-person collaborative motion prediction task. Okay, so this is a global pipeline of our work. So let's start. Let's divide it into different steps, and we first take one sequence of a sequence of one person at first. So following a previous work called LTD, we first focus on the last observed frames and use a discrete Gaussian transformation to embed the temporal information of the last frames, and use a graph convolutional network to embed the spatial information, which means the different joints of one frame of the person, and get a result, get a first result. And then we follow a previous method called history repeat itself. And we look into the longer past, and we divide the past into several different subsequences, and use a attention block to get the weighted result. So the main idea here is to look into the longer past and find the most similar past subsequences with the current observation and the possible future. So this is for one person, and now we go into two person, so we do a sample copy-paste. And now we have two models in parallel for the two dancers in our data set, and they are separately and do not share weights. And then we build up a link block. We call it XIA, which is cross interaction attention. And this block is based on sample multi-head attention. And we use this block to use the information of one person to guide the learning of another person. So do not go to more details here. And now, this is the global idea of our pipeline, our method. And now, with the help of our collected XPi data set, we can try to test the performance of our result. So for the XPi data set, we have designed different testing training splits on it, and we also designed two different testing matrices for this data set. And now we want to compare our result with previous state-of-the-art single-person motion prediction methods. But all these previous SOTA methods are designed for single person. So when we want to compare with them for fair comparison, we have to decide how to implement these methods on our dataset. So for each method, we have tried the 3 different implementations. The first one, mix, means that we consider our 2-person dataset as a 1-person dataset, and we mix all the all the 2 datasets together and train one single model by any state-of-the-art method. And the second one, concate, means that we concate these 2 persons together as a big person, which means that if one person has 18 joints, now we have a big person of 2 times, like 36 joints. And the third one, separate, means that it's very simple. We just train 2 different models for each person. And on all the methods and all the splits, the third one performs the best. So in the comparison of our method with previous ones, we implement all the state-of-the-art method by the third implementation. And here are some numeric results. Our method has overpassed all the previous methods on all the splits and all the evaluation methods. So we just skip this and look into some visualization results. Yeah, here we can see here are some visualization results comparing our method with previous methods. And the light color is not very clear here. It's the ground truth, and the darker color is the prediction result. We can see ours is better. And let's look into some video results, which might be more clear. And we can see there are 2 samples here. Each one have 5 samples here. The first 4 are previous SOTA methods, and the last one is ours. And there is a bar here showing the changing of pose error in each frame. Yeah. So we can see that our result, well, the darker colors of our results, which is the prediction result, is close to the light color, which is the ground truth. And even we can look at the red sample, we can find that in many challenging, interesting results, in many challenging actions where the previous methods totally fail to predict the future, our methods can still get the global tendency of the movement. So this is for the first work. And then let's move on to the second one. It's a very simple method for single-person motion prediction. So why we present these works together is because when we are starting the first project we just presented, we found that in the literature research, we found that in the recent 3 years or 4 years, most of the works for human motion prediction is there's a trend that these works are aiming to design more and more complicated networks to model the spatial and temporal information, especially the spatial information of the human motion. But so we wonder, is this really necessary? Because we think their motivation is not very clear why they want to use more and more complicated networks. So let's look into this figure for more, to be more clear. So this figure shows the number of parameters in x-axis and the pose error in y-axis on human 3.6M dataset, which is the most popular 3D human motion dataset. And here is a comparison of different methods. So some years ago, some early methods have used RNN-based or convolutional-based methods like this to do this task. But we can see the results is not very satisfying. And in 2019, a method called LTD, we have just mentioned it before, it has started to use graph convolutional network to model the spatial information of the input data, motion data. And it has improved, it has overpassed the previous methods for large Morgan. And after this work has appeared, in the recent 3 years, most of the works are following this work or inspired these works. And many of them are designing, are also based on graph convolutional networks, but they are designing more and more complicated and heavy networks to do this task. But it's always based on graph convolutional networks or sometimes transformers. But the main idea is always try to embed the spatial and temporal information, but the network is becoming more and more heavy. So we start to wonder, is this really necessary? Because we know that the motion data is quite simple. It's just a sequence of human skeletons of several joints. So we wonder, are these complicated networks really necessary? So we just did two very simple naive tests, which is shown at the left top, the purple joint repeating last frame, and the blue one, 1FC. Here, the repeating last frame means that we take a sequence of input observation, we repeat the last observation frame several times and take this directly as output. So this is very stupid, but we can see the numerical result is not that bad. And then the 1FC experiment means that we take the input motion sequence and we just use one FC layer on the sequence on the temporal dimension. And we can see that we already learned something interesting here. So based on this observation, we designed a very, very simple network called Sample, and it's based on MLP layers. Oh, sorry, it doesn't appear. Okay. Yeah, we designed a method called Sample, and it's just based on MLP layers. Yeah. And this is the pipeline of our method, and we can see that our pipeline only combines these sample blocks, the discrete Gaussian transformation, the first FC layer and the last FC layer, which operates on the spatial dimension, and several MLP blocks. Here, the MLP blocks consist of a FC layer operates on the temporal dimension, and a layer norm. So here, the layer norm is the only block in our pipeline which is nonlinear. And also, during the application studies, we found that the most important thing here is the MLP block, which consists of the temporal FC block and temporal FC layer and the layer norm. So if we change the first FC layer and the last FC layer, which operates on the spatial dimension, to temporal dimension, so which means that we have no spatial merging, then the performance will only drop like 2 millimeters. But if we change all the FC layers to spatial merging without any temporal merging, the performance will drop like 25 millimeters to 30 millimeters. So we can see what is the key idea here. And we have tested our result on 3 different data sets. And our work, our model always performs the best than all the state-of-the-art methods. And more importantly, our model is much more lightly than the previous methods. So let's come to the conclusion. We have presented 2 works. The first one for multi-person motion prediction, and the second one a rethinking for the single-person motion prediction, which propose a simple but strong baseline. So now on, after these 2 works, we are still doing some further follow-up works about human motion, because having this simple but strong baseline, we are thinking, of course, if we can do something similar for 2-person without such a complicated network as we have just presented in the first work. So we have to do some very early sample easy experiments on 2-person using the model we presented in the second paper, and we can already got the state-of-the-art results for multi-person motion prediction. So we start to thinking, or perhaps the network itself is not very interesting. So with a very simple network, we can also do many things. So perhaps we can think of doing something else, something further, not focusing on the network, but on the presentations or some more interesting tasks. So if you think it's interesting, please follow up our future works in our team. And there might be some new results in the very near future. And so I finished my presentation, and for the 2 works I just presented, the code and the data I just mentioned are all available. And here are the QR code for the 2 works. So if you're interested, and please scan it, take a photo, and if you have any questions, you can now ask me, or afterwards you can also contact me by email. Yeah, thank you.
Thanks. So any question from the audience?
hi. Nice presentation. I have few questions. As you said that for multi-person, if a scene has more than 2 persons, so I think your system cannot have been confusion between them.
Yeah, this is a problem. As we have explained a little in our paper, because here we just tested on 2 persons. It's because our data set just has 2 persons. Because it's collecting such a 3D human data set is very difficult. It needs a studio and needs some very professional actors. So and it's dancing is just for 2 persons. So in this data set we just have 2 persons. But the pipeline here is designed. Because it's on this data set, so we just have 2 parallel model and a linked block between them. So it's for 2 persons. But if we want to imply it on more person, in a more person scenario, one simple thing we can do is to put them into 1 and 1 couple. So for example, if we have 3 persons, we have 2 couples of them or 3 couples of them and implement this model directly on it. So that will be a possible solution.
Okay, thank you. And the other question is, if for occlusion problem or background problem, if we cannot detect few joints of the skeleton of a person, so in that scenario, what will be the result? Like, what will be the model do?
In fact, in the motion prediction problem, we don't use RGB videos. So the input is directly the 3D data. So there's no occlusion problem in this task. So, but yeah, occlusion is a big problem in, like, if we want to detect the pose or the motion from RGB videos, that will be a big problem. But it doesn't exist in this task. Yeah.
Okay. Thank you. Thank you so much.
You.
Okay.
Okay, so we are running out of time. So let's thank the speaker again. Okay, so I think that now we have a coffee break and then we can continue. Thank you.
¿Este va? Hola. Se oye, ¿no? Sí.
Hello.
Sí, bastante, porque si no...
Ya, pero igual no quieres estar aquí así, ¿no?
No, mejor más dinámico.
Y este yo he visto acá... Hola. ¿Se sent o no? Sí, no? Hola. A ver...
Hola, hola.
Hola, hola, hola. Hola. Vale.
Okay, let's get started with the last session of the day. So my name is Amaia Salvador. I'm an applied scientist at Microsoft, and I'm going to be the chair for this session, which is going to be about multimodal learning. We have 3 papers today, so let's just get things started. So the first speaker that we have is Juan Montesinos, and he's going to talk about a paper that's called, I hope I say this right, VoViT, Low Latency Graph-Based Audio-Visual Voice Separation Transformer. So the floor is all yours. Go ahead.
Hello, everyone. I'm Juan Montesinos, and I'm glad to be here in another edition of this Barcelona Deep Learning Symposium. So, as Amaia mentioned, I'm going to talk about this paper, Low Latency Graph-Based Audiovisual Voice Separation Transformer that we presented in ECCV this year. So, for those who are not familiarized with the task of audiovisual source separation, it's very simple. It consists of isolating voices presenting a mixture of sounds, leveraging the visual information of the target voice. So to give you an example, this is a real-world video from YouTube, and it may look something like this. So here we have 5 voices and 3 instruments as accompaniment, and we could be interested in isolating the voice from the guy within the box. So in fact, this can be tackled from an audio-only perspective, which usually works very well when there is a single singing or when there is a single voice. And that's because voices are very different from instruments, but when there are several voices, then they tend to be overlapped in the frequency, so that's much harder. Also, audio-only methods tends to work worse in noisy environments, for example, in bars or clubs, maybe concerts. On contrary, audiovisual methods, as they leverage lips motion, they usually overcome these issues. But of course, we don't want to double the computational cost of our algorithm. And as you all may know, processing video is very expensive. And the main difference between this work and other works is that instead of using raw video, we use 3D face landmarks. So 3D face landmarks are something like this. They are a graphical representation of the face. And in fact, as they are 3D face landmarks, we can consider them as a point cloud, and we can find a rigid transformation, which means we can orientate and translate these face landmarks in the space as we want. So, as we can do that, there is a very fancy application, which is, okay, given a frame and the registered landmarks, we can align and standardize the point of view by rotating the face. We can also consider these face landmarks as a graph. So I'm not going very into details of graphs, but it's a set of edges and nodes. So the dots are nodes and the green lines are edges. And if we combine these 2 things, we have a very powerful system. So for example, given a frame like this that may not be very common in our data set, we can estimate the face landmarks and normalize the point of view. So standard point of view are usually good for overfitting. But also note that we are dropping the appearance, right? So we are dropping the face, everything, but the motion, which is very good, for example, to be robust in terms of gender or ethnicity. Also, of course, helps to reduce overfitting. It's also robust in changes of illumination. And it's also very private, right? Imagine this is a cloud-based system. We could send the data to the cloud, and we are not disclosing our identity. Also, okay, video consists of, even if this image is small, 256 by 256 or whatever, it's already some million data points. On contrary, landmarks are a few hundred data points, again, overfitting. But at the same time, as they can be considered as graphs, we can use graph convolutional networks to process the information and get meaningful representations. So, okay, it sounds very good, but are any disadvantage? Of course, these face landmarks are an estimation from the video, and the question is if they are as powerful as video, or if they are good enough to carry out these tasks. So that's what we are trying to solve here. To give some foundations on source separation, the general pipeline looks something like this. So we usually don't work with 1D signals, although some works does it nowadays. Instead, we have a short-time Fourier transform of the signal, which means we have a 2D matrix, a complex matrix, which stands for time and frequency. So we feed that into a neural network. And our goal is predicting a mask that in this case is a complex mask. So the fact it is a complex mask means we can modulate the magnitude and the phase of each time frequency point in the input. And the idea is that if we multiply this mask by the input, we are going to obtain the isolated voice. Another challenge in source separation is that recovering or gathering real-world datasets is very complex, because that means we need to be capable of recording sound from different sources without interferences. This is without hearing each other, which is pretty hard. So when we have large-scale data, what we do is creating artificial mixtures. And in audio is as simple as zooming them linearly. Maybe we can add other artifacts or other resources to model better the sources. But that's pretty much the idea. In the end, we have each individual source, and we have the mixture, so we can have the ground truth. And well, by the end of the day, we are minimizing some sort of distance between the mask and the network whose inputs are the spectrum and the visuals. The way we propose to solve this is via this transformer, which actually has 2 stages. So the first stage is purely audiovisual, and then we have this sequence of landmarks. So this is like video of the landmarks, and we are processing it with spatiotemporal graph convolutional networks that are going to extract temporal information from motion. Then we concatenate the audio features, time-aligned, right, from here, that we extract with an encoder that preserves temporal dimensionality, and we feed them into a fancy transformer that is going to predict the aforementioned mask. So this transformer has a module called ST encoder that you may not be familiarized with. It stands for spatiotemporal encoder. And basically, or in short, we are transposing the input using 2 normal or standard transformer modules, and then transposing back and zooming. That's the idea. So again, the loss function is some distance between the mask and the ground truth mask. And of course, this works somehow. Here we already have a very good estimation of the isolated voice. And we could scale up the network. We could add more data to improve the results. But we do a different thing. Instead, we have a second stage, which is a purely audio-only refinement. So the idea here is, OK, if here there is a very good estimation of the voice, so that means we can hear the isolated voice plus some interferences. What we can do is run an audio-only process that may be iterative to refine this. But what we found is that instead of using an Euclidean distance like this, for example, if we use other type of masks, these are binary masks, so they can only modulate the magnitude. If we use these sort of masks as binary cross-entropy loss, this is like a boost, right? So we are removing a lot of interferences at a very cheap cost, because this network is tiny compared to the other one. So trying to answer the question that we posed, are phase landmarks good enough for this task? We evaluated this in VoxLab2, which is a YouTube-based data set. It's not very good quality, but it's very large scale for the standards, for the open source standards. It has 2,000 hours of video, and what we show is that well, Visual Voice is previous state of the art. They try to exploit appearance. They also use raw video, motion. They use everything possible. And we show that in terms of overall quality, or maybe this SDR stands for the reconstruction of the 1D signal, it's very comparable, or they are the same thing. However, in terms of SIR, which stands for interferences from other sources, our method works much better, and that's thanks to the second stage that I mentioned before. Let's see an example. So this is a real-world computation in the US.
I'm just glad that I've been able to remember they were Mexican. I didn't know that. I didn't know that. And they didn't know that I didn't know that.
So we are going to try to isolate the voice of this guy here. And this is how the energy looks like. This is the mixture. And this is the prediction of the state-of-the-art network.
I'm just glad that later on I found out they were Mexican. I didn't know that. I didn't know that. And they didn't know that I didn't know, and that's...
And at the beginning, there are many interferences. We don't know why, if it's due to the occlusion of the microphone, the side view, the blur. But this is our result when we use phase landmarks.
I found out they were Mexican. I didn't know that. I didn't know that. And they didn't know that I didn't know.
And if we compare them side to side, we can see that within the first 2 seconds, our network is capable of filtering out the other speaker, while the previous state-of-the-art can't. And we see here much less energy. That means maybe the network is filtering out more stuff, although this is future work to analyze the reasons why. And we also tried this in a very small data set, and I can tell you the takeaway from this is, okay, if you have very few data, phase landmarks are good. So this is 46 hours compared to 2,000 hours. Well, let's see an example. Oh, yeah, baby, whip it to me. This is another approach or baseline. Yeah, baby, whip it to me. That despite the audio quality is not very good, you can hear it have a lot of interferences. And if we use this approach with 2 stages, oh, yeah, baby, whip it to me, the quality improves a lot. We also try to check whether we can use networks trained for speech separation in singing voice, and the answer is no, it's not a very good idea. And that's pretty much all. Thank you for coming, and if you have any question, feel free to ask.
Cool, thanks a lot. Do we have any questions for the speaker? Just checking quickly. If not, I do have a question. So I was wondering, so are these metrics evaluated per person? So you have one, so are you checking how good is the quality for, if there are multiple people in one video, you will evaluate individually?
So the typical approach is that these videos or these data sets are already curated. In case of Box Select, for example, the faces of each person is already extracted.
Right.
And we also don't have real-world data set to try, real-world mixtures to try this on. So we really evaluate on artificial mixtures as well. That's where the metrics come from. Mm-hmm. So we can only show a showcase with real-world data.
Yeah, makes sense. And so what are your thoughts? Because what I was thinking is that so it can happen in a video that there's, so people are shown, but they don't speak, and then voices are heard that you don't see the person. So what I was thinking is it would be cool if you just input a video and then it outputs, okay, here's the 3 people that are speaking and here are their voices. But it can happen that you cannot see them, but the voices are there or vice versa. So have you thought, or maybe you can brainstorm right now on how, because that's a first step, but then you would need some furniture around what you propose to make that happen.
So the idea is that these algorithms, or in case this paper is trained with a single face, so you could feed the network with many faces, but it only gives a small improvement. On contrary, it's more versatile to use a single face and try to isolate the voice of that person. In case you don't have the face, what the network usually does is exploiting biases. For example, in the singing voice dataset, most of the singers are female, and if you don't really pass meaningful leaps, what the network does is to overpredict women. That's a little bit the idea. But of course, if you don't have the face, then you are in an audio-only scenario, which is different, and you have to play a permutation problem where you try to estimate all the voices and so on.
Right.
And that's more
it's a whole different problem, yeah. Okay, any questions? Last call for questions for the speaker. Okay, then let's thank him again.
Thank you very much.
Okay, so the second speaker for today's last session is Ginger Delmas. I'm going to give her some time to plug in the laptop. Okay, so as I said, so Ginger Delmas from UPC, the Institute of Robotics, she's going to talk about PostScript, 3D human poses from natural language. Go ahead, the floor is yours.
So, hi everyone, I'm Ginger, thanks for the introduction. And this is a joint work with Philippe, Thomas, Francesc, and Gregory for both IRI here in Barcelona and Naval Labs Europe. So, language and vision have long been a hot topic, for example, with works like Clip and DALI. And here we are interested in language and 3D geometry, which is becoming quite crazy these times. And more particularly in language and 3D human poses. So you could look at motion or you could look at static poses, and we will be more interested in static poses. So as you can see here on the right, there is the downward dog yoga pose. So if you don't know what it is, you can get an explanation here on the left. So basically you have the 3D human pose here, and then the explanation saying that, okay, in the downward dog, the yoga pose, the head is down, the arms are stretched straight forward, the feet are foot apart, and the legs are straight. So it's pretty interesting to have the two together, because then you get a semantic understanding of the pose, of what's going on, of a fine-grained understanding of the body parts relationships. So once you have the two together, this opens the door to a number of applications. So for instance, you could search for complex poses in large-scale datasets. So let's say you have a huge database of 3D human poses. You want one in specifically, but you don't want to scroll down this whole page of 3D poses, so you could just write a description of it and get it, for example. Something else, you could do it for digital pose generation. So instead of designing all the body parts of the 3D body for animation, you could just write the description to get a good initialization, for example. This could be used as well as a pseudo 3D annotation. So when the deployment of mocap system is not very possible, for example, here the woman is on the mountain. Well, you cannot really do that in the studio, right? So perhaps if you give a description, you can get already a good approximation of the 3D pose. And again, for pose teaching, for example, you can give instructions to the person who is going to do the exercise, and yeah, it's pretty interesting to have the relation between the text that is describing the pose and then the pose itself. So yeah, we are looking at language and 3D human body. So language can take several forms. It can be binary relations. For instance, here is the left hand above the hips. It can be labels. For example, here the action label sprint. Or it can be natural language. And we will focus natural language because it's more intuitive and very natural way to convey ideas. It's very flexible, so it's not constrained to closed vocabularies, for example. So when you look at some previous work on natural language and poses, they usually use other visual cues, like other poses. So if you take a sequence of poses and natural description of the sequence, well, the natural description will correctly constrain the whole sequence, but you won't know information about the specific poses in the sequence. So that's why we introduced PostScript, which is a new dataset linking 3D poses and natural language. So it's made of 3D human poses extracted from this huge dataset, AMAS, of 3D human poses. We collected human written descriptions from Amazon Mechanical Turk, so which is an annotation platform. So basically, we showed the annotators the pose to annotate and 3 other poses that were quite similar to the first one. And we asked them to describe the pose to annotate, like here it's the blue pose, such that the description only fits the blue pose. The idea was to have a description that is discriminative enough so that when you retrieve the pose, you are sure that you have the one you wanted. And since human annotations are expensive, we also developed this automatic generated pipeline to generate more descriptions. So basically for each caption, we generated 6 automatic descriptions. So I'm going to present this automatic captioning pipeline. So as input, it takes the 3D human pose, and more specifically, the 3D key points on the pose. And we compute some pose configuration, like we will compute the angle, for example, of the right elbow. We'll compute the distance between 2 body parts, for example, the feet. We will compute the relative distance as well as between body parts and so on. And once we have these measures, we classify them and interpret them. So, okay, perhaps the right elbow is bent at the right angle, for example. The 2 feet are wide apart. Yeah, so these kind of things. And when we have this elementary information about the pose configuration, we can also combine them into higher level concepts. So for example, if the person has the 2 feet bent, well, the person is leaning, very probably. So we can obtain that like this. And once you have all this pose information that we call pose code, that's a lot of pose code. You don't want to describe about all of them. So we will select them. We will remove trivial pose codes, for example. So the fact that the left hand is at the left of the right hand, this is most often the case, so we don't really care about that. We will also randomly skip pose codes, because when humans write descriptions, they often forget a lot of details, for example. Remove redundant pose codes as well. And once we have this set of pose code, so that we have a concise description, we will aggregate, and so we have more natural description. So basically, we merge pose codes based on shared semantic between them. So let's say you have information about the left knee, information about the right knee, and the same information. Instead of saying twice the same thing for the different knees, you would say, okay, the same information is applying to the two knees, so the two knees are bent, for example. So it's really basic stuff like this. And then we plug this postcode information into template sentences, so you can obtain a structural description in natural language at the end. So there are some polishing steps and stuff. So to give you an example, in this data, this captioning pipeline is highly modular. Like you can define many different aggregation rules, many other selection rules if you want as well. It's randomized, so we applied some randomization at several steps in the pipeline, so you can generate plenty of different description for the same pose, and it's cheap. Like we can generate 60,000 description in the times it takes to actually write one, so it's really nice to have it for data-hungry algorithm. So yeah, to give an example in this data set, let's say you have this 3D pose here, and this human written caption. So for example, the person is bending backward as if they are dodging bullets in the Matrix. Well, of course, the automatic captioning pipeline doesn't do that. But it tends to be more precise and give more details. So for example, the right knee is forming an L shape. Yeah. So once we have this data set, we do two things. The first one is text-to-pose retrieval. So the idea is that you have this text that you write, and you will retrieve 3D poses. Basically, rank all poses from a data set by order of relevance to this query that you add. So let's say you have this pose and this text from the PostScript data set. You will encode both of them into a joint embedding space and force with the contrastive loss to have the two embedding close together in the embedding space. And at the same time, because it's a contrastive loss, you will push elements from different pairs far apart in the joint embedding space. So at the end, the idea is that if you query with the text, you will encode it in the joint embedding space and retrieve poses whose embeddings are close to the embedding of the text, because they are supposed to be relevant. So here's an example. Okay, so someone is sitting with their right leg crossed and hands are folded on the lap. So here are some examples that we obtained with the model. And you could do the same as well for images if you have 3D human fits for images. So basically, we run the same algorithm on the 3D human fits, and then we just return the image. So yeah, that's why the context can vary a lot, because we are really here interested in the pose and not the context. So that's the first thing we did, and then the second thing we're going to do is text condition pose generation. So basically, the main difference with text-to-pose retrieval is that here we are not looking for a pose that already exists. We are going to generate it from scratch. So at this time, what we have is this text that we wrote. We will encode it, but this time as a distribution, so you can have some variability when you generate the pose. And then we will sample a Z vector from it and decode it as a pose. So that's how it works at test time. You have this text and you generate the pose. And at train time, it works a bit like a variational autoencoder. I mean, it is a variational autoencoder. So you would encode as well the initial pose, like the correct pose for this text, as a distribution, sample from it, decode it as a pose. And then you'd have this reconstruction loss between the two poses to ensure that you are actually generating plausible human body poses. We will also have this scale divergence loss between the two distributions to be sure that the text and the pose are aligned. And moreover, we will have this regularization loss with the normal Gaussian, so you would be able to generate poses out of the blue without any conditioning. So here are some examples for text condition pose generation. Let's say the left elbow is bent at a square angle. Here are different poses. Yeah, the left arm is the left arm of the body, not yours. And so the more detailed the caption, the less diverse the generated poses. So take-home messages for this work are that PostScript is a dataset of 3D human poses with human written description and automatically generated descriptions. We used it to do text-to-pose retrieval model and a text condition pose generative model. And last, we showed that better performance can be obtained when we pre-train on the automatic caption than fine-tune on the human written captions generated by the automatic captioning pipeline. So yeah, that's all. Here's a small demo, but you can ask questions in the meantime if you want.
Thank you, Ginger, for the very nice talk. Any questions for the speaker? There's a question over here. Give you a second, and I'll give you the microphone. 1 second.
So for pose generation, not every pose that is expressible as XYZ coordinates is actually physically possible. So I wonder whether there is some kind of automatic filtering, or whether that was part of the model, that it was generating poses that are possible.
Yeah, so we don't enforce any constraints on the poses to be sure that they are plausible. There are previous work that basically does it without condition and text, so it's a variational autoencoder on poses called vPoser, and they do not enforce any rules on this later either, and it still work. I think it's also due to the date set, because we feed it with plausible poses only, but you could add this constraint as well, and but we didn't notice any monsters so far, so that's good.
Okay, thanks.
Other questions? Okay, yeah.
Hello. Thank you for the presentation. I would like to know if there is a possible way to bend things that are not meant usually to be bent. For example, maybe the spine. I know contortionists may be able to do that, but not the usual people. Or maybe the neck, or, you know.
Yeah.
So do you take care of those kind of things? Can you describe them in your algorithm?
Yeah, okay, so you could still describe this if you want, but spoiler, I think the model won't work for very extreme poses. Okay. So it's really tied to the scene the scene poses in the data set. That's true. Yeah.
Okay, thank you very much.
That was a really cool presentation, thank you. And my question is, there was a part where you explained about the automatic captioning generation, right? So, like, on one hand you have a human like that's giving the description for it, and then on the other hand you have like a generation part which is done. So, and you said like there are multiple variations of the same pose that you can generate through it. So, I mean, like, how do you evaluate if that automatically generated caption is correct?
Like because you say there are several generation possible, so how do we know if they are correct?
I mean, like, in general, when you create those automatic descriptions, how do you know it's right? Like, how much of it is right? Is there a model that already does that, or did you do that part of it also in some ways?
So it's really, so this captioning pipeline, if you really want to cry in front of code, you can open the code for that. It's basically if else all the time. So it's really controlled. Like you can be sure that it's correct in that sense. Now it's true that people can have different interpretations for a post configuration. Perhaps this is white for me, but this is not white for you. So, but this is controlled with like hyperparameters. So, and there's this randomized threshold as well, so to have different.
Okay, and one last question. So, and like, if suppose for the same pose there are like 10 different captions that are available, and when you like train it, and like through that, if you're trying to like search for one of the pose, like which one of these captions are considered? Like, is there some weighting thing on which one is given more importance, like when searching for it? Because there might be similar poses that might fit that description, but you know,
yeah, it's true. So for the human written caption, that's why we showed the 3 other poses to the annotators to enforce the discriminativeness of the caption. But for automatic caption, you could generate as many as you want and still randomly skip lots of information. So yeah, probably the caption won't be unique to the pose. So for evaluation, if that's also part of your question, we basically rank all the poses for each of the automatic caption and make an average of it.
Okay.
Like it's a recall measure.
Okay, thank you.
Cool.
Thanks a lot.
Let's thank the speaker one more time. Okay, so we're in for the last talk of the day. So the speaker is Margarita Geleta, and she's going to present the work called Pix in WAV, Residual Steganography for Hiding Pixels in Audio. Go ahead.
Thank you, Amaia. Hello, Barcelona. A small disclaimer, I just landed from a transatlantic flight a few hours ago, and I'm completely jet-lagged, but we have an exciting talk ahead. Today I'm going to present a recently accepted paper in ICASP, the International Conference in Acoustics, Speech and Signal Processing, titled Pix in WAV, Residual Steganography for Hiding Pixels in Audio, which was co-authored with my collaborators, Cristina Punti, Kevin McGuinness, Jordi Pons, Christian Canton, and Xavier Giró Nieto. For the ones who are not familiar with the term of steganography, we'll see that in a minute, and then we'll dive deep into the gist of the paper. So steganography is quite similar to cryptography in a way. I'm sure all of you are familiar with cryptography. You're using this every day when you are logging into your devices. You have a password, and this password is a secret token word that everyone around you knows that it's a secret, but it's encoded in a way that's computational and feasible to break it. However, in steganography, no one is aware that you are actually hiding something. The existence is the secret, so only you and the intended receiver know that there is something. To give a visual example, let's have a look at this Leonardo da Vinci's Gioconda. Do you see any difference between both of these pictures? Maybe if you're quite watchful, you may notice some pixel differences, like color intensities or some pixels that are different. But if we take the difference between both pictures, we will end up uncovering a secret military base picture. This is a basic example what steganography is. It's a really bad example because just taking the difference, we've found out the secret. So it's actually bad. And this example is quite good to introduce the trade-offs, the three goals that we have in steganography in general. And these three goals are usually antagonistic. In the best case, we can achieve two of them. Three of them is actually really difficult. So the first one I have already mentioned is the transparency, which is we try to avoid suspicion. So in the example of the Mona Lisa, we actually saw these pixel differences and we were suspicious, that's why we took the difference. So that's one goal. The second goal is robustness. If we send the picture of the Gioconda face through a channel or we compress it and then decompress, we will be able to extract the military base picture. That's the robustness goal. And finally, the embedding capacity. How many information can we actually hide in one face? Can we hide 1 pixel per channel, or how much information can we hide? And all that is the unimodal setup of hiding an image in an image. Pix in WAV introduces a multimodal idea, which is hiding an image in a waveform, an image in an audio. And this is more challenging because it introduces additional constraints, because sound is it has a different nature than image. And Pix in WAV also has the feature that it uses deep learning. That's, to our best knowledge, this is the first method that has been actually tried out in a real controlled lab setup. We'll see that later. The idea is the following. If we have a waveform, we convert it into a spectrogram using a mathematical transform, which can be Fourier cosine basis based. We have used the discrete cosine transformation. And the image is encoded into acoustic low power noise using a hiding network. And then this noise is residually added on top of the spectrogram. Once we have the spectrum with the image on top of it, we can use again the mathematical transform we used in the first place and convert it back to the waveform. We send it to our friend at the other end. The friend decodes it with the mathematical transform, gets the spectrogram, and uses the revealing network to extract the image back. That's the whole pipeline. How is it trained? We use 3 different losses. The first loss is the image reconstruction. It uses the L1 norm between the original image, the secret image we want to hide, and the revealed image at the end. The second term is the L2 norm between the spectrograms. So the spectrogram that we use as a the spectrum where we hide the image and the spectrum with the hidden image within. And finally, we use an additional loss for temporal alignment, which is the dynamic time warping between the original waveform and the waveform with the image encoded within. So that's the whole system. What about the experimental results? We present two types of experimental results. The first one is trying everything in the computer. So we do all the transformation in the computer without taking the sound somewhere else. That's the first one. We'll see the second in a minute. The results are actually really good, especially if we use the dynamic time warping. You can see that in image, we use the structural similarity index. It's quite good because it's about 0.9. It gives really good reconstructions in the image if you look at the visual results. And regarding audio, it's also quite good because the average is about 18 decibels in signal to noise ratio. And no suspicion at all is usually about 20 decibels. The weak point of PixInVav is robustness, because as I just mentioned, we have high signal to noise ratio and SSIM values, so perceptual transparency is good. Embedding capacity is also actually good. You can see all the calculations here. We can hide a lot of information, but robustness is the weak point. Can we somehow try to solve this? There are ways we can train, including noise during training time. So here you can see an example. If we train without noise, the reconstruction is way worse, rather when we train with noise. This is something that hasn't been explored in depth, but it's an avenue to explore, and further research can be followed in this line. And now the second experiment that I mentioned, actually trying it in a real room. Disclaimer: we haven't analyzed any filters that the microphone or the speaker can have. We didn't also take into account the background noises in the room. We just try this in the field and see whatever happens. So this is what happened. We're trying to transfer through air these baboon and pepper pictures using some sound as a carrier. And this is the result, what we got at the other end. Actually, almost everything has been lost, but you can see something still has been preserved. You can see that, for example, there's a green and red barrier between where the nose starts and ends in the baboon, and also some differences in the foreground and background peppers, really slight. But the interesting thing is the misalignment. So if we try to decode a misaligned section of the waveform, so the red side is the misalignment, it actually captures really well where the image has ended. So it really sees where the image information starts and ends, even though it doesn't decode really well. So that's a really interesting experiment. It shows that the method is feasible. It's a new way of information transmission, but it still needs more research. It's just a start. So, to recap, we presented, to our knowledge, the first deep learning-based multimodal steganographic model to hide image in audio, and that has been actually tried in a lab. And if you scan this QR code, you can hear some samples. I didn't risk myself to try to put the audios here in the room. You can try it later. And that's it. If you have any questions, I'm all yours. Thank you.
Thank you, Margarita. Any questions? Okay, there's one there.
Hello. Did you consider adding reverberation to your training process so as to improve the results in your real-world experiment? Because I guess that most of the degradation there is because of the reflection with the room.
In this work, no, but there's another student that continued this work, and he actually tried. He has a bachelor thesis on this.
Good.
Any other questions? 'Cause I do have a question in the meantime, because it sounds like, if I understood correctly, this falls into the like unlimited data for training paradigm, right? So you need images, you need, I'm not sure if you need audio. So I was wondering on what data you trained on, and if you explored, if you checked like how much data you need, because in theory you can, if you just need images, you can take as many images as you want.
That's a good question. We had limited resources. So we used a specific number of images from ImageNet. For sounds, we used the Noisy SDK, I think it's called, dataset. And it has any kind of noises from different instruments, really anharmonics sounds. Yes, but we used a specific number of images and audios. It's specified in the paper. It wasn't unlimited. We had constraints.
So do you expect that this would help if you would go to larger data sets, or if you could, I don't know, like virtually you could do it with any image data set and any audio data set that you can find? I mean, I understand that this was a constrained setup, but would you expect, I don't know, for instance, would this training on more data, would it improve, do you think it would improve on the last experiment that you checked, like the real scenario?
I think so, because the data set we used for sounds, it didn't include many voices, so it was just
sound, yeah.
Yeah, sound. So I think it doesn't generalize on any kind of sound, so definitely yes.
Cool, very nice work. Any last questions before we wrap up? No? Okay, let's thank the speaker one more time. Thank you.
Thank you.
Okay, so I think this is the end. There's Cava and Turrons, I believe. Am I saying it right, Xavi? I think you're coming. You want to talk? You.
Okay, yeah, this is the end of the oral sessions. Thank you everybody for attending. Now there's still a poster and Turrons and Cava session. It's back at the Sala Agora. That's where we already were before. If some of you were not there yet, just ask me or any of the volunteers, because we must go back to the UPC Campus North, okay? So thanks for attending.